Hey, thanks. I also want to thank David and Noam for organizing this the workshop, and Yossi for the long-standing collaborations. I think I actually met Yossi when I was a grad student, when you visited Cornell, maybe. And then a postdoc. You also visited when I was a postdoc with Lieber. So we sort of go back even farther than the 2005 SRC grant with David that was mentioned earlier. But because this is a workshop, sort of getting to know one another, I'm treating this basically like an advertisement, an overview of what we do, not going into depth on any one particular topic. But the general interest in our group, as I mentioned, is in low-dimensional materials. We have work on quantum dot systems, nanowires, nanotubes, as well as 2D materials. And these are just examples from different groups around the world. And what we notice about each of these is we do studies on individual nanostructures where you can essentially count the number of atoms across the structure that we're actually going to measure. So emphasizing that with modern fabrication technologies, too, we can also electrically contact individual nanostructures. And that provides a basis for a lot of the characterization that we do. So what are the few of the opportunities that we see, both in terms of science and technology? First is mainly exploratory. So we want to explore novel properties in low-dimensional materials. And a good example of that, of course, is graphene, where there's a recent awarding of a Nobel Prize for basically novel physics. On the chemistry side, we're interested in using new synthesis techniques or hybrid synthesis techniques to make novel heterostructures. Just it's something that's new, it's interesting. And then really as material scientists, we're looking for qualitatively distinct structure property relationships that occur. So maybe unexpected phenomena in nanostructures or heterostructures of distinct low-dimensional materials. And I'll show an example of that later. Some of the challenges, of course, is that, well, nanostructures are very small, right? And it sounds trivial, but really when we're trying to interrogate individual nanostructures, it's not necessarily trivial. And in particular, as material scientists, we're interested in elaborating structure property relationships. And there are well-known techniques, microscopy techniques, for understanding structure and composition. Some of the demanding challenges are linking those to the properties of individual nanostructures. And I think we'll see some nice examples of this type of work from Laurie Marks later today as well. So in the end, some of the more specific challenges we have with low-dimensional materials include doping, the effect of surfaces, making ohmic contacts, and interrogating heterojunctions. And of course, you have the same challenges in thin film materials, but some of them are essentially exacerbated when we make the structures really small. Okay? So how do we approach this? It's essentially an integrated approach involving the synthesis of new materials, nanoscale analysis of structure and composition, what we call functional imaging, which is an attempt to resolve properties with high resolution, and then understanding the behavior in devices through modeling. And so I'll talk about some 1D and 2D materials, techniques including atom probe tomography, which David introduced, as well as TEM. And the point here of integrating these two activities, of course, is to essentially establish connections between, in this case, processing and structure. That continues with functional imaging, and I'll talk about scanning photocurrent microscopy to establish connections between essentially nanostructure and properties. And that often happens within a device context. So if we can make devices of these materials and model them appropriately, we actually learn something about how the local properties are connected to device properties and sort of macroscopic measurables. And now ultimately we sort of aim to close the loop and have the device performance feedback on synthesis. So my talk will really have two parts. First, I'll talk about relatively older work and some of the collaborations with Yossi that have really gone through this whole cycle for semiconductor nanowires. I'll then turn towards newer work in 2D materials where we're sort of at the beginning of this process. Okay? So beginning first with nanowires and thinking about some of the opportunities to make new structures and observe new properties, we use this vapor-liquid-solid growth method that Yossi and David alluded to, in which a vapor source of a semiconductor precursor feeds this liquid alloy, resulting in precipitation of the solid semiconductor at the liquid-solid interface. And this process was defined some time ago by Wagner. So of interest, of course, in semiconductors is controlling their conductivity through impurity doping, which we do chemically through the catalyst, and then also in defining heterostructures by, again, controlling the chemistry of the precursor and alternating that in the gas phase, producing, in this case, axial heterostructures. So we wrote a review article to sort of summarize the opportunities for nanowire heterostructures that I'll just refer you to for the sake of time. But I want to begin with the characterization of nanowires by atom probe tomography to sort of take you through this cycle and past work. And we really needed this technique, and we're very fortunate. I was fortunate to land at Northwestern, where we had this atom probe tomography, to be able to do this. So on the left is an SEM image of a slightly tapered nanowire. And if you look at it in the atom probe cross-section, you can see that there's this gold catalyst at the top. And in this case, these are blue-colored germanium atoms. Okay. So looking at this in 3 dimensions, it highlights that we can image buried interfaces. That's one of the powerful aspects of the technique. And we can do so with atomic resolution, which you can see by examining these 111 planes that occur in the center of the reconstruction. So this is a nice internal calibration as well for the technique. Now we turned our attention to doping fairly early, to understanding dopant incorporation processes. So this is a slice through the germanium nanowire that's been grown in the presence of phosphine, which should be an N-type dopant. And what we found is an enhanced concentration of phosphorus towards the outside. And if we look down the center of the wire, you can get a better sense of the geometry. Essentially, there's a less doped region in the middle, a more highly doped region in the outside. Quantitatively, we can extract profiles from the center to the outside, put numbers on it. And what we learned from these experiments was essentially that this VLS portion that was precipitating out of the gold was not as heavily doped as what we call this vapor-solid region, essentially the deposition on the side, which is much more highly doped by a factor of 2 orders of magnitude here. Okay? So the atom probe enabled us to understand something about the dopant incorporation kinetics that differed between these 2 different processes. And that's important because you can see if I go from one end to the other end of the nanowire, it's becoming more doped, so more conductive. Now to see that on the functional side, there's a couple approaches one can take. One is scanning photocurrent microscopy, which we did in our group. So now we're looking at silicon, but the same phenomenon occurs. This is an optical microscope image, and below this is an image of the photocurrent. Okay, so without going into great detail, what you see in this non-uniform channel response is essentially a variation in resistivity. The brighter regions where you're getting more photocurrent are more resistive, so they're more responsive to illumination. And it's telling us that the potential drop is not uniform. We're getting a greater potential drop here in the less doped region. So this is, in essence, an image of this surface doping process that can be made even more quantitative by combining these SPCM measurements with Kelvin probe measurements, as we did with Yossi. So with this additional understanding of inactive versus active dopants, we could tailor the synthesis conditions and produce, in this case, a more uniform response in the device channel, a linear potential drop across the material. And again, in this case, feedback synthesis, the device properties back into the synthesis conditions. And so these are a couple papers that, again, we worked on with Yossi, essentially explaining what was going on in this context. So as we were studying this dopant, I would say the studies were not without their surprises. This is sort of continuing work in which we tried to isolate further the VLS from the VS doping. And so we're going to look at a part of a nanowire here with atom probe tomography in which this region was grown without any dopant flowing. So the only dopant can really come from whatever's dissolved in the catalyst. Okay, so that's the germanium nanowire. This is the transition where we turn off all the doping. And this is the phosphorus. You can see it sort of decays past that point because this is just what's coming out of the catalyst. And the surprise to us is when we looked at this region here, after removing the dopant source, we got something that was highly non-uniform. We sort of expected uniform precipitation out of the catalyst. That's not what we saw. And if you look at a concentration plot, there's even these distinct peaks that show up that look like they reflect the crystal symmetry. So after some time, we came to understand that indeed this doping out of the liquid was highly non-uniform. It occurred primarily at the interface. And some of that understanding came from in situ measurements in a couple other groups, as well as working with Peter Voorhees to do some modeling. And what we came to understand is that the growth interface is not this single 1-1-1 interface, as we thought in sort of the cartoon form. It actually has multiple facets. And so the dopant incorporation rate depends on which facet the dopant is coming in through. So of interest, in particular to those in making devices, is that this is an enhanced surface doping, essentially. And that's done intentionally in semiconductor devices to lower the Schottky barrier and thin the Schottky barrier to make good ohmic contacts, as illustrated here. So essentially going from A to B is what happens when you increase doping near the surface. You get a reduced barrier. So to show or explore what was going on in nanowires, we turn to this photocurrent imaging technique again, now going below the band gap and going into the infrared, where you probe metal, electrons that are excited from a metal contact over that Schottky barrier. So this is a sequence of photocurrent images now focused on the contact regions as we go to longer wavelength, or lower energy photons. You see that current is fading. Quantitatively, if we extract that dependence, we see that the yield, or the square root of the yield, depends on energy, as one would expect for a Fowler model of internal photoemission over that barrier. So this fit essentially enables us to extract the Schottky barrier, which, as I mentioned, is dopant concentration dependent. Okay. And so taking into account what we measure in atom probe, and Yossi's measurements of the active dopant concentration, which turns out to be much less than the physical dopant concentration, we input that into a device model, Centaurus, to calculate these potential profiles and see how they match up with the photoemission measurements. And we found we could reproduce trends in the barrier height with diameter from left to right, and also with different doping levels by combining, again, atom probe, the Kelvin probe, and the internal photoemission measurements. So we find that, as expected, the doping lowers the effective Schottky barrier height. There's a strong diameter dependence that arises from geometry. And then, in addition, there are interface states whose occupation influences the barrier height. And so we've now extended this basic approach to look at silicon and oxide photoanodes, which are of interest in photoelectrochemical cells, where, again, surface doping, dipoles, and interface states control the efficiency by which you can oxidize water, which is sort of part of this cycle of converting essentially water to fuel using sunlight. So this is just sort of a retrospective analysis of how we've tried to integrate different activities to really understand what's going on in the materials. So this partially motivated, intellectually and just understanding connections. On a practical side, we feel like this provides a solid quantitative foundation for device engineering. So I'd like to point out a couple of the applications that seem more promising for nanowire type materials. So there's been a lot of interest in photovoltaics, going back to a proposal by Harry Atwater 10 years ago to make radial p-ion junction solar cells. And more recently, there have been some developments in solid-state lighting with a couple companies commercializing LEDs based on a nanowire architecture. And I think the way to think about these opportunities in general is that they're non-planar heterostructures. So we saw several years ago CMOS transition from a planar device architecture to a non-planar device architecture, really to continue scaling. And there are some benefits also in LED applications for going non-planar. Again, I don't have time to elaborate them in detail. So I'll just mention some work that I won't have time to talk about involving using atom probe tomography to map the composition in core shell nanowire LEDs. We also ran these as solar cells and used the photocurrent mapping to essentially spatially map quantum efficiency and understand how that related to the photonic structure as well as the electronic structure. We've done some analysis on more conventional planar InGaN LEDs with collaborators at Rensselaer Polytechnic Institute. And then finally, more recent unpublished work on 3 arsenide nanowires, where the interest there is in high-performance transistors, and we're using atom probe to analyze the delta doping in MOSFET structures. Okay? So I just put a few references up there. Happy to talk about that in the breaks or at dinner. A few other results or body of work I'm not going to talk about is in oxides, because I've read in the program there is some interest in oxides here. So we spent a few years looking at VO2 nanowires and studying the metal insulator transition by various means. So we did some work using Raman spectroscopy to track the structural phase transition while measuring it electrically in devices. These are in single nanowires, looking at suppression of the insulator to metal transition by controlling stoichiometry. More recently, nanomechanical measurements So looking at the mechanical properties of essentially single nanowire cantilevers as they go through the phase transition. There's some really interesting dynamics and changes in how the photons behave. And then using that same kind of methodology, we've recently been looking at molybdenum disulfide resonators, detecting their motion optomechanically and really showing that we could get these into the strong coupling regime, which is of interest to a certain community. So if anyone has interest in these areas, again, I'd be happy to talk about it, but I won't have time to talk about it today. I would like to transition, though, to recent work on 2D materials, some of which is published, some of which is not. And so just a very brief introduction. We'll probably hear more in the next talk. Of course, pioneering work on graphene really has excited people's interest in a range of 2D materials with very different properties. Molybdenum disulfide has been probably the most studied semiconducting 2D material thus far. And just a recent review by Deep Jariwala, who's a grad student of Mark Hersum's, and Tobin Marks, who's really fantastic, has talked about the interest in digital logic. So these are competitive for some other materials classes that are used in essentially a more lower performance ubiquitous electronics. So not as a CMOS replacement, but more broadly. So the community at large, of course, has made pretty much any kind of device you can imagine by this point out of the molybdenum disulfide. So sensors, photodetectors, transistors, et cetera. Okay. So that's great. But what I think we're more interested in the work at Northwestern is what can you do that's really different? And so Mark Hersum's group has really pioneered this idea of vertical p-n junctions in ultra-thin materials that have qualitatively distinct behaviors. So Mark is going to talk about that, I'm sure, tomorrow. But just to introduce the idea, this is a device in which molybdenum disulfide in purple here is deposited, and then sorted semiconducting carbon nanotubes are put on top. So we have an N-type on the bottom, P-type on the top. This is a top view of the device. So that's a p-n junction where the gate field is vertical to the device. And so it has this novel anti-ambipolar behavior, this green curve here in which, as a function of gate, the current goes up and then back down again. And again, I'm going to let Mark talk about that because it's really the concept that his group has pushed. And we've been involved in sort of trying to understand the underlying device physics and how far this concept can be pushed. So I'm going to talk about not this vertical junction, but another kind of unique lateral heterojunction that occurs when you do this Scotch tape method of exfoliation and sticking down 2D materials. You find that sometimes you get to transition between a monolayer and a bilayer. Now, if you've seen these plots or heard how the band structure evolves as you make MOS2 thinner and thinner, and in fact it goes from an indirect to a direct gap, you could ask yourself, well, if this is an indirect gap semiconductor and that's direct, what kind of junction do we have? Okay. So if you put contacts on such a device, as in here between a 1-layer and a 2-layer device, you see that it's rectifying. Okay, so whatever's in the middle there at least has rectifying characteristics. But what we don't know is whether the band alignment is type 1 or type 2. Okay. Either one might produce such a rectification. So what we've done is to apply the scanning photocurrent microscopy, where instead of just measuring a current and a voltage in the dark, we measure current and voltage as we scan a laser across the device and look at the response of the junction distinct from the channel or the contact. Okay. So here's some scanning photocurrent data. So going from left to right, we go between a contact to the junction to another contact, and then the different color curves are different biases. Okay. So what you see is there's a pretty significant response at the junction. It changes polarity with bias. Okay. And we did some finite element device modeling based on materials parameters that were extracted from devices of uniform thickness. Okay, so we use that as input, and just to summarize, in a device simulation, we're able to reproduce, at least qualitatively, and I would say semi-quantitatively, the response of the local response of this junction to the photocurrent. Okay. So what comes out of this simulation, or what underlies it, is actually a band structure. Okay, so we're using basic materials parameters, computing band alignment, we're able to reproduce the photocurrent map, but then also the rectification characteristics. So for us, this is a way, again, of using a local probe to try and reconstruct the band alignment at one of these novel heterojunctions. And this is something that's in revision at this point. We've been working hard to get it published. Okay, so for the last couple minutes, I'll show you two more works. So we've transitioned in the group from working on the exfoliated material to actually growing it by CVD. And so one issue we looked into recently is that of stoichiometry. So we're ultimately interested in controlling carrier concentration and doping. We also need to understand how stoichiometry affects things. So left to right, there's examples of MOS2 flakes from 3 different growths where we're decreasing the amount of sulfur exposure. We see that if we look in XPS, there's a decreasing sulfur peak, which essentially corroborates or correlates well with the synthesis conditions of reduced sulfur. In transistors, if you focus on the black line here, we saw that surprisingly, at least at first, the field effect mobility increased with decreased sulfur content. Now, I'm not going to explain this in detail, but it arises from the fact that we still have a large number of defects in this material, and we believe that the sulfur vacancies effectively dope it so we can get above a mobility edge. Okay? So that's kind of, we're in the midst of really exploring the basic properties of the material. But what's more interesting about these particular defective materials is that when they're sulfur deficient and they have grain boundaries at a particular geometry in the channel, they show memristive behavior. So I think Mark will probably talk a little bit about this as well, and I won't go into it in detail. But in contacts where there's a grain boundary within the channel, you can manipulate that grain boundary and see essentially a memory effect. So there's a certain bias at which the device turns on to a higher conductance, and it will stay there upon decreasing the voltage. Okay, so this is the foundation for what is called memristive behavior with reasonable on-off ratios. And it occurs in devices, as I mentioned, with grain boundaries and sulfur vacancies. So it's really a challenge to us at this point on the material side to understand how to control that through the synthesis conditions, because there's some interest here in exploring these devices for neuromorphic computing. So we all know that neurons somehow store memories, and you see a memory effect here. But what's really different here is that these are sitting on a gate voltage as well. So there's a third terminal that can influence how strong the response is, right, between these 2 terminals here. So this is an architecture which essentially is a better mimic for some of the processes that happen in your brain than silicon. Yeah, in vacuum. So just to wrap up, I talked about the motivation for us of sort of this closed loop approach of correlated imaging. But I'd say in nanowires, we've kind of demonstrated what we'd like to do. And in 2D materials, it's very early stages. So I highlighted the challenges of doping and defects to control carrier concentration and mobility. Again, still pretty much early stages in the CVD growth of MOS2. There's heterogeneity at multiple length scales. So we have point defects and vacancies. We have grain boundaries of different orientations that influence electrical properties differently. And in a device, right, micron scale is much larger than these point defects. So we have to understand structure at multiple length scales. On the modeling side, that brings in the challenge of integrating essentially a quantum treatment at the atomic scale of the materials together with continuum models that are suitable for explaining the device characteristics. And then finally, we're still at the early stages in terms of being able to reproduce a material of a particular stoichiometry, and also bringing in the challenge of ohmic contacts, which, again, always a challenge in semiconducting materials, and in 2D materials, a pretty active area of research. So these are the areas we're sort of looking at in the future. I think there's a lot left to be done despite all the recent activity in the area. And again, look forward to talking with any of you who have similar interests. So just, the point I wanted to make here is that these are a number of important challenges. It's a pretty broad scope of work, and that it's really important challenges that motivate collaboration. So to wrap up, let me just point out again some of the collaborators on the 1D, Yossi Rosenbach and Peter Voorhees, and then with David and Rui Yerushalami on the contact doping, and the 2D materials, Mark Hersom and Tobin Marks. And then in the 3.5s, George Wang, Christian Betzel, and Gregor Kobelmuller. And thanks again for your attention.
Questions, please? Yossi? I didn't understand what's the role of the grain boundary in the memory effect?
So the grain boundary is resistive. So if you have a grain boundary that bisects 2 electrodes, you see a potential drop there. Okay? But the grain boundary is also correlated with a distribution we think of sulfur vacancies, which are conductive. So it's not simple to explain, but we've looked at how bridging, so between electrodes, bisecting, and then this other geometry of intersecting grain boundaries influences the electrical characteristics. Okay. And we've observed that they move. So Mark's group has seen them move in EFM, and there's some other imaging evidence of that. We don't yet understand, so we can control the motion with a bias, but we don't understand all the details of what's moving. It does move, yeah. Yes. So under bias, right? Good suggestion. Yeah. So some obvious next steps, because these were unencapsulated, unpassivated devices, right, is to start to intentionally modify surface chemistry, which is something that, on 2D materials, something that Mark's group has done quite a bit of. Of the junctions themselves, we do. If the we also includes a group at Purdue of Mark Lundstrom, meeting with them in a week and a half to go over the initial results on that very structure.
There's some indication that the step edges of the edges of the graphene molecule is involved. And so do you have any feeling for whether the bulk properties are going?
Right, so in the MOS2 bilayer, yeah, single layer bilayer. So what we did, right, is look at single layer devices and multi-layer devices, and actually we can reproduce the device characteristics using essentially a 3D density of states and effective mass model, but incorporating the electrostatics appropriately, so in finite element modeling, right? So electronically, treating them basically as 3D, but in the simulation you take into account the geometry. And we can reproduce the junction characteristics. Now that's not to say that in perfect materials, in vacuum, right, at low temperature, there are more things going on. So there are groups looking at the transport properties along grain boundaries, because you get a little confinement potential there. And also there's going to be here uncontrolled influences of adsorbates, so an important direction in the future is actually to control the surface chemistry to have a better defined junction, basically. So that really does need to be done.
But you're worried about the passivation or chemistry of the edge. Yeah.
Mm-hmm. It's different.
That's very hard to characterize. Basically now it's one-dimensional picture.
Yeah. So indirectly, that's where we've used the electrostatic force microscopy, so similar to what Yossi has done, to confirm at least where the potential drop is occurring between our electrodes, right? But it's a coarse picture that says we have the basics right, but there's a lot still going on that we haven't brought into the analysis.
Elon, perhaps you missed it. Don't remember. Was it a monopolar or bipolar stitching? Can you put that to
Yeah, there is. I think the full curve is shown in the inset there. And there's a lot more supplemental data as well. Yeah.
What is A and what is B?
So A is going up, okay, so voltage increasing, B is going down. Okay, so B would be the more conductive state, or the on state, right? After you've exceeded the set voltage, which there is around
That
Eight
one
volts.
looks like monopolar, but in the ESET,
Yeah, right, right. So it looks, you do have a bipolar behavior in the inset. This is just amplifying what's seen on the positive bias side.
I had one comment and a question to make about grain boundaries. One is there's a large literature on grain boundary mobility, and a generality that comes out of that, the lower the angle, the lower the disorientation between the grains, the higher is the mobility. It's one generalization. The other generalization is impurities on the grain boundaries affect the mobility. And also there's a literature, it's small, on measurement of grain boundary mobility in magnetic fields. Here you're in an electric field. But you could see why they probably are low angle boundaries, because the atom movements, you can identify dislocations in interface. It's much easier for the atoms to move in a low angle boundary than in a high angle grain boundary. So the structure of the grain boundary is going to affect the mobility. Can you measure the mobility?
In principle, you could. Here, there's an electric field. There's also a current, right? So there's heating, but also the potential for electromigration, which is sort of what you might expect in the context of heating by Joule heating. Okay? So it's not necessarily that straightforward. I think, to my knowledge, there's been one measurement of grain boundary motion that's atomically resolved in a TEM, where the essentially energy has come from the beam, right?
That's thermally activated.
Yeah, they could actually verify that grain boundaries can move, and that was actually helpful for the revisions in this manuscript to convince the reviewers that indeed they could move, because in this first study we'd not looked at that systematically.
Yeah, because grain boundary mobility depends on temperature also.
That's right. So in most of these cases, memristive behaviors where you're moving mass, not just charge, but you're moving mass around, there's some thermal process. It's not just, it's never exclusively a field, right? But it's thermally activated, and then that's when you have to take into account the Joule heating as well, and the temperature profile across the device.
so you have any evidence of thermophoresis? Serrated?
I don't think so. Thermophoresis?
Nico was talking about Rutschner thermal plants.
You can get mass transport in a temperature gradient.
Yeah, but thermophoresis is a particular mass transport. Towards the gradient, so the Serrated effect is all.
You need a big temperature.
They
Yeah.
go to the large temperature.
So in these devices, we've done the IV characterization in vacuum, in Mark's lab, EFM in air. Yossi had some early devices to look at Kelvin probe actually in at least a dry environment, where that's what I would want to use as the basis for starting to look at particular mechanisms, because if we can measure the potential drop under the conditions where we're getting the motion, that would be very helpful in modeling of the temperature profile as well. We haven't done any direct measurements of temperature. Potentially we could do it with Raman. We've done that in nanowires, but really haven't tried to do it with the 2D materials, using strain to measure temperature gradients. But that's an interesting suggestion, and I'd like to hear more about the isolation of the mechanism.
Here you go.
Just one comment may I add to David, that low dimension interaction of them on the surface also affects the
Yeah. So here the surface is the edge of the flake, I guess, right? Because it's all surface here, and then there's a grain boundary, and then the edge becomes a surface. So it's a 1D surface.
Okay, thank you very much, Lincoln.